So hello everyone. Today let us discuss about materials, which is first chapter in our Codal provision IS 456 2000 Codal provisions. We'll discuss about cement, aggregates, and concrete. In concrete technology, we go in deep into the properties, how it is manufactured, how constraints influence the parameters like strength, etc. But now here we are discussing what is required basics for reinforced cement concrete as per Codal provisions. So cement, what is cement? Cement is a combination of argillaceous material and calcareous materials. So what is this argillaceous material? Argillaceous material is like clay, shale, etc. There's this calcareous materials like lime, malt, etc. Like when we combine them and burn together at high temperatures like about 1450 degrees centigrade in kilns, they fuse and forms a clinker. So finally when this clinker is formed, we grind it by adding gypsum. So what is gypsum? It is like a retarder which is used to prevent flash setting of cement. So to prevent that setting of cement immediately after mixing with water, we add gypsum, the final stage, or how much we add, like 2 to 3% of total clinker nodules. We add this much percentage at the end, the grinding stage, to prevent flash setting. So next, coming to manufacturing of the cement. Cement is manufactured in we call them as ball mills or tube mills, and we deploy two methods. One is wet manufacturing process and second one is dry manufacturing process. What is this wet process and dry process? Like wet process is this raw material like limestone fragments and clay, they are ground to slurry with the addition of water. This is the main thing. In wet process we add water to form slurry. In a dry process we grind them into fine powder in dry state without adding the much water. Like and say in second step in wet process, this slurry is stored in tanks, and we will keep it in constant agitation, because this raw materials with heavy particles will get settled down and lighter particles like water will come up. So when constant agitation we store them in tanks, and after that we feed them into rotary kilns where the temperature is some around maintained for 50 degrees centigrade for fusion to take place. In this rotary kilns, material rolls down from material rolls down from top to bottom and get at the lower end at high temperatures, gets fused and turns into clinker of size 3 mm to 20 mm. So this is the brief manufacturing process of cement. And what is main difference is, in wet process fuel wastage is more, because we are adding water, and finally for the formation of clinker nodules fuel which we use is more. In dry process, that we can save this. And when we come to types of cement, based on the requirements of the cement in the place which it is being used, and like by varying constraints in the cement, have different types of cement. First one is ordinary Portland cement, OPC. Like we have 3 grades in it: 33 grade, 43 grade and 53 grade. So what is this number 33, 43 and 53? These are characteristic strengths in Newton per mm square at 28 days. So normally how we test cement for compressive strength? Normally we prepare cement square blocks size 7.07 centimeters because the surface area should be 3 mm square. Based on size is 7.7 70 mm size, we make this cube. We prepare it with the cement is to the ratio 1:3. Prepare this cube, and when we test it at 28 days, what is the compressive strength? That compressive strength is 33 Newton per mm square. Then we call it as 33 grade OPC. If that number is 43 and that strength is 43 at 28 days, then we call it as 43 grade. If it is 53, and then we call it as 53 grade OPC. So how this number varies is, this number this compressive strength depends on fineness of the cement, mainly fineness of, if fineness is more, heat of hydration is more, and heat of hydration is more, the strength that gains is more. And so if fineness is more, the strength gain at 28 days will be more. Then from here we can infer that 53 grade OPC has more strength and more fineness when compared to 33 grade OPC. This is about OPC. And second one is rapid hardening cement. So rapid hardening cement is, in the name itself we can say this, this is used where we want a setting and hardening of the cement to be faster. So how this rapid hardening is achieved is like, so what is this rapid hardening is, we all know about Burgess compounds. What are they? There are 4, like C3S, C2S, C3A, C4AF. Based on the composition of the cement, like how much percentage, the cement properties varies. So if C3A is more, setting of the cement and hardening of the cement, like early flash gain of strength will be more. So for rapid hardening of cement, we need this C3S and C3A to be more and less C2S. So why C2S should be less? Because here it has low heat of hydration. It is responsible for low heat of hydration, slow gain of strength, and when C3S and C3A are more, it will be rapid rate of hydration and rapid strength. So in rapid hardening cement, what is like, C3S should be lesser and C3S and C3A should be more. So why this rapid hardening cement is required? Suppose if we are repairing roads, and if we want to remove formwork very early, in that case that cement should get hardened very quickly. So in that cases we use this rapid hardening cement, and to obtain a rapid hardening cement, we have to increase C3S and C3A, and we have to reduce this C2S component. Second one and third one is here Portland Pozzolana cement. So if we require this higher workability at lower water content, or if we need some specific like a parameter from cement, then we consider this Portland Pozzolana cement. What is this Pozzolana? Pozzolana means it is like siliceous material. Pozzolana is siliceous material, and it do not have cementing properties on its own. That is very important. do not have cementitious properties on its own. It gains this cementitious properties, like means binding property, only we add it to cement, and it combines with this pozzolana combines with cement hydroxide, which is liberated during heat of hydration, and based on that this siliceous material gets cementitious property. And where this is used, Portland pozzolana cement is used in the places where high workability is required at lower water content, and comparatively the gain of strength is slower rate, but slowly the ultimate strength is like similar to OPC only. That is the earlier it got up to 25% of the total percent. So it is like about 35% of the total we are replacing with Barcelona components. So normally in IS 456, like we have fly ash, a few pozzolanic like GGBS, are artificial, and we have natural cementation, sorry, pozzolana materials, the ball clay, kaolin, so rice husk. So these and all are we can use for to add, like pozzolana materials we can add to cement to get desired properties. And fine, we have this low heat Portland cement. Is this low heat Portland cement? Low heat Portland cement is where heat of hydration is low, and why this heat of hydration, when this heat of hydration is low, we have this slow gain of strength. So rapid cracks can be avoided when there is this slow gain of strength in heavy constructions like dams, retaining walls. Like when mass of the structure is huge, so in interior part of that structure there is chances of developing cracks when there is rapid release of heat of hydration. So in that places we use low heat Portland cement, where there is slow gain of strength, and where this cracks can be avoided in structures. And here finally we are discussing the slab sulfate resisting Portland cement. This sulfate resisting Portland is used where if our cement has like C3A and C4AF, this aluminum, this reacts if in external environment, if there is sulfate, this alumina reacts with sulfate and develops material which results into disintegration of cement. So in the environment where there is chance of sulfate is present, we use this sulfate resisting cement. So what we have to do, as this sulfate C3 and C4AF are the main materials reacts with the sulfate, we reduce C3A and C4A, get sulfate resisting cement, and we use cement mainly in the underground construction where there are possibility of sulfate attack, and we use them in marine structures. So here to like make the cement resist to this sulfate attack. Then have this size of aggregate related to aggregates, like have to refer IS 383 code book about testings and all. In IS 456 reinforced cement concrete, what is the maximum size of aggregate that we can use is given as like maximum size, nominal maximum size should not be greater than 1/4 of minimum thickness of the member. If is the thickness of the member like minimum 3, if the size of aggregate is we use G, that size of aggregate this should not be greater than, if it is the minimum thickness, 1/4 of the thickness. Like if we aggregate, it should not cover the entire thickness, it can cover only up to 1/4 of the thickness. So next, heavy reinforced concrete beams, the maximum size should not be greater than minimum clear distance between main bars minus 5 mm or minimum cover to the reinforced section minus 5 mm, whichever is smaller. Suppose if we consider a beam and it is like singly reinforcing bar, and this is the clear distance, if it is the clear distance between the main bars and if it is the minimum cover to the reinforcement, like maximum size of the aggregate should not be more than this minimum clear distance between the main bars minus 5 mm and clear cover 5 mm and this clear cover distance minus 5 mm and should be not be more than smaller value is 2. Suppose if minimum clear distance is 3 mm, 20 minus 5 is 15 mm, and if clear cover is 40, 40 minus 5 is 5 mm. Minimum smaller value between this is, so maximum size of aggregate which we can use here is lesser than 15 mm. That is the codal provision related to maximum size of the aggregate. Then have concrete. In concrete, first thing is compressive strength. We all know that concrete is strong in compressive and weak in tension. Compressive strength. What we take this compressive strength at 28, the characteristic compressive strength of the concrete. Characteristic strength is strength below which not more than 5% of the test results are expected, which means like if we have this M20 grade concrete, 20 is the M is for mix and 20 is the characteristic strength, that is compressive strength at 28 days. So if we take 100 samples and 95 samples will have characteristic strength more than or equal to 20 and only 5% of the samples will have characteristic strength less than 20. So in that case we can say that this 20 is the so we can say that characteristic strength of this sample is 20 Newton per mm square and the grade we designate as M20. Here normally code book we have 3 types, so it is grouped into 3 types. One is ordinary concrete, second is standard and high strength concrete. So ordinary concrete is up to M20. From M25 we call it as standard concrete, and from after M55 up to M55 standard concrete, and after that from M60 it is high strength concrete. Normally we use this codal standards up to M55, and after this to use this from M60 we required separate experiments and all ground level data everything. So here one more thing I want to add is like minimum grade of concrete in limit state design is for reinforced concrete is M20, and this M10 and M15 these are for plain cement concrete or lean concrete without reinforcement. You can use 10 and M15. And if it is reinforced structures and we are designing it in limit state design, means have to use from M20. And we all know this about batching of the concrete, final mix and dry batch concreting. So this nominal means we can use for ordinary concrete, and for standard concrete we should batch by volumes, and we have to weights for batching of the testing. Then have this tensile strength of the concrete. Normally tensile strength we have to measure it like tensile strength the Q use like compressive force. Here it develops like tensile cracks. We have to test this by user mentioned in IS 516. But in case like RCC, this and this procedure, and if we cannot follow, then we can infer the tensile strength, flexural strength from compressive strength. We are not like doing this experiment and all finding this flexural strength from whatever FCK characteristic strength is there. We are finding this flexural strength. What is the formula given? FCR equal to 0.7 root FCK Newton per mm square. In competitive exams and all, this can be used as like one question. For example, if they ask like to find flexural strength of M20 grade concrete, we can say this flexural strength FCR equal to 0.7 root FCK. Here FCK is 20 Newton per mm square. So we can do it like FC 0.7 root 20. What is the answer? We can find out this formula, flexural strength. Then second this thing is modulus of elasticity of concrete. So with respect to steel, whatever the grade of steel is, like Fe2, Fe 415, Fe 500, irrespective of grade of steel, we have this modulus of elasticity Es equal to 2 into 10 to the power of 5 Newton per mm square. It is constant and it does not depend on the grade of steel in case of steel. But in case of concrete, this elastic modulus depends on grade of concrete. It varies with the grade of concrete. Because with grade of concrete, characteristic strength varies, and EC depends on the characteristic strength. So in concrete it is not same for every grade of concrete. It is short term static modulus without considering the effect of creep into account. So this also can be asked for 1 mark like in competitive exam. So if it is like M25 grade concrete, FCK is 25 Newton per mm square, and modulus of elasticity EC we can find like 5000 root 25, means 5000 into 5 equal to 25,000 Newton per mm square. So like this, if they give grade of concrete and ask us to find modulus of elasticity, this is the formula. These are very important. These two formula is like flexural strength. Modulus of rupture is also FCR equal to 0.7 CK. Modulus of elasticity, this is short term modulus. If they ask for a long term modulus, then we have to see that E effective equal to EC by 1 plus theta, where theta is the creep coefficient. So we can find out effective modulus of elasticity from short term elastic modulus divided by 1 plus theta, where theta is creep coefficient, and this creep coefficient depends on age of the concrete. So normally next, shrinkage. We all know what is shrinkage. If there are, while we prepare the concrete consists of water, and when this water gets evaporated, this concrete will develop air cracks. If water content is more at the beginning, cracks, cracks. Yes. So This shrinkage depends on constraints of the concrete, how much water is there, how much cement is there in that concrete. So shrinkage depends on constraint of the concrete, size of the member, surrounding environmental conditions, how much humidity is there, temperature is there, like it depends on all these conditions. But it is mostly influenced by the amount of water present in the concrete at the time of mixing. So if it is more, shrinkage cracks will be more, and it also depends on the cement concrete. So one thing we have to see is in types of cement, OPC, we saw 53 grade OPC. In this, shrinkage will be more than 33 grade cement. Normally in concrete also, suppose if we add more cement content for more to obtain higher strength because of high heat of hydration, if we use like M30, will have more shrinkage than M20 grade concrete. Shrinkage not only depends on amount of the water, but also the cement content present in it, because cement is mainly responsible for this high heat of hydration in the concrete. So total shrinkage strain in the absence of any data, we take it as 0.003. But for clear parameters and all, they are mentioned in our pre-stressed concrete code IS 1340. All the how by taking base also into account, shrinkage varies. Here in RCC, if there is any for absence of data, we take it total shrinkage strain equal to 0.003. Sometimes in exam they will also ask like this, 3 into 10 to the power of minus 4. Have to remember this for total shrinkage strain equal to 0.003. And creep also depends on this constraints of the concrete, size of the member, everything. And in addition to this, it also depends on age at loading and duration of the loading. We all know creep is like deflection or deformation at constant loading. We are not changing the load. At constant loading, what is the deflection that is taking place? We call it as creep. Suppose if there are two electric poles, there is wire here, electric starting when we tie this wire will be straight only. After few years, it gains this sag and will appear like this. We are not adding this extra load, only self weight of the this wire remains same, and after few years it gains this shape. This is called creep. At constant loading, with the time, what is this deformation taking place, deflection from the superficial axis, this is we call it as creep. So creep mainly depends on age at loading, and it depends on duration of loading. Creep coefficient, we have this formula, creep coefficient equal to ultimate creep strain by elastic strain. And in code book we have this creep coefficient for 7 days, 28 days and 1 year, and this is very important for the exam. Simply they ask like creep coefficient for 28 days, we have to pick 1.6 creep coefficient for 7 days, 2.2 creep coefficient here, 1.1. What is this ultimate creep strain? Ultimate creep strain is when we take this creep also into effect. Elastic strain means like when there is without considering this creep into effect, what is the strain caused by the loads, we call it as elastic strain. Creep coefficient equal to ultimate creep strain by elastic strain. If in exam they give this elastic strain, and they mention, if we not directly, they give like age at loading some 1 year, and they ask to find out ultimate creep strain. So we can find ultimate creep strain equal to, for 1 year creep coefficient is 1.1. So 1.1, they mention what is the elastic strain in the concrete. So if we multiply this, we get this ultimate creep strain. This is important for the exam. Have to remember this table. of creep coefficient. So they can ask directly, or they can ask to find giving either ultimate creep strain or elastic strain. They check whether we know this creep coefficient at age of load. And this is for today. For next class, let us see what is this limit state design. Before that, combination of loadings. After that, we'll start main structural parameter structure elements like beams, columns. For IS Codal project, we'll take next class also on IS Codal project. Then we'll start beams. Thank you.